Okay, let me get that unfreeze. Okay, so a little exploration here. We've got Legos. We have 8 small bricks, 6 large bricks, and we're going to call these our raw materials, in which we want to build chairs and tables. Okay, but we want to make the most of. It froze again. The most of what we have. Okay, so work with your table mates and discuss how many chairs and how many tables should we make. What? Yes. So what are our thoughts?
Two tables and 2 chairs. 2 tables and 2 chairs.
2 tables and 2 chairs. If we make 2 tables and 2 chairs, do we end up using all of our raw materials?
Yes.
Yes, so then we have nothing left over, okay? All right, so this is sort of like what we're going to be doing in today's lesson, linear programming. So again, one of our warm-up problems was graphing a linear inequality. And the point is, because we're going to work with that and sort of with this exploration, maximizing or minimizing different topics, okay? So when it comes to linear programming, alrighty, again, we have a system of linear inequalities, and we call those constraints. And then what happens is we graph all of those inequalities, and we look for a region that's overlapping that satisfies all of the linear inequalities. So we satisfy all of the constraints. And so what happens is anything that falls within that overlapping region, we call the feasible region. So any combination of numbers in that feasible region will satisfy all of our constraints. But again, our goal is to go for a maximum of something or a minimum of something. Often it's a maximum profit, okay? Sometimes if we're doing minimizing, we're trying to minimize the cost of something. Okay. And all of those maxes and mins always occur on the corners or the vertices of our feasible region. And that's what this corner point principle is about, finding the maxes and mins at the corners, and then we test them. Okay, so the corner point principle, what happens is for every linear programming problem, we have what's called an objective equation, okay, or an objective function. So again, often that objective is to maximize a profit. Right. So in this example here, our objective function is k is equal to 3x plus 9y. This one has already been graphed for us. Okay. So what happened here is we had constraints. We already graphed them, right? So this was a constraint here. There was a line here. This was a constraint. There was a line here. This was another one. There was a line here. And then because we are dealing with contextual items, physical items, we're not going to work in the negatives. So everything gets graphed in the first quadrant. And so it's sort of automatic that everything falls in here. Okay. So again, all this yellow area happens to be the region where all of those were in common. All of those constraints, the linear inequalities, all have something in common. Yes?
Is the feasible region yellow?
Yes. Yeah, this is all the feasible region. So let's write that down. Feasible region. So again, anything inside here will satisfy all of the constraints. But again, we are after an objective. Our objective at this point is we want to maximize this equation here. Okay, so this is what we're going to call the objective function. And so again, maxes and mins always occur at the vertices of our feasible region. So that means we've got this point here, this point here, 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 and here. Those are all of our vertices, and one of those contains the maximum. Okay, so I usually just kind of start in the low left corner with that 0, 0. What's going to happen if we plug 0, 0 in?
It's going to be
Okay.
low.
It's going to be 0. We're after a maximum, so I'm not even going to waste my time testing that one. And then I'm just going to kind of go around. Okay, if I plug in 0, 2, if x is 0 and y is 2, that's going to give us k is equal to, what's the objective function in? 3x plus 9y. 3x plus 9y. So we would get x is 0, so that would be 0 plus 9 times 2 is 18. Therefore, this would give us a quantity of 18. Our next one, 3, 4. Just going to plug in 3, 4. So this would be k is equal to 3 times 3 is 9, plus 9 times 4 is 36. We get an output of 45 for this one. We have another point at 7, 3. So 7, 3. So again, k is equal to 3 times 7 is 21, plus 9 times 3 is 27. This one gives us an output of 48. And our last point is 9, 0. And that's going to give us k is equal to 3 times 9 is 27 plus 0, so we just get 27. Okay, so now that we have all of them stated, we can see which one provides the maximum output. 7, 3 is that combination, yes. So this is the max.
Whoa. I kind of didn't see that table. Do you have to make a table?
No, you don't have to make a table.
Oh, okay.
No.
I was just kind of working out each problem.
Yeah, no, you don't have to make a table. We're not going to make a table as we do these.
Okay.
This is just to build us into the understanding of what the feasible region is and what we're testing. Okay, are we ready to dive into one from the beginning? No?
I like that one.
Where it's already set up for you? Yes, Allison?
I have a question about just like the problem.
Yes.
Okay, so actually, can you scroll up a bit?
Back up this way.
Okay, so what you first did, were those points already there?
Yeah, so this one was already set up for us, but we're about to do one from the beginning where we're going to find everything.
And the feasible region is like the place like inside all those points?
Yes.
When they're connected?
Yes, the yellow region.
Okay.
Okay, it all overlaps. Okay. All right, so here is our first problem we're going to do from the very beginning. All right, so we have a manufacturer of calculators. They produce two different models. They have a scientific model and a graphing model. All right, the company wants to know how many of each model should be produced to maximize the profits. So first thing I'm going to do is I'm going to go ahead and give a variable to each of my, I guess, items. Okay, so I'm going to go ahead and name my scientific S and my graphing G. All right, so the scientific model yields a profit of $25. And the graphing model yields a profit of $50. We want to write an objective equation to represent the total profit the manufacturer will make on a combination of the two types. So again, the objective function is to maximize profit. So we're going to have a, bless you, profit equation is equal to 25S, correct, plus 50G. All right, and again, this is our objective function, and the objective function does not get graphed. Okay, we come back to this after we're done graphing. Okay, so now we have to look at all the constraints. Okay, so to meet demand, the company needs to produce at least 200 of the scientific calculators. At least 200. So I need to set up a linear inequality there. Scientific calculators needs to be at least, so greater than or equal to 200. So there's one constraint. Also, at least 80 of the graphing calculators. So what would that inequality look like? Greater than or equal to 80. Okay. Okay, also, the largest daily output possible is a total of 400 calculators. So what is that inequality?
This in like one day.
If we're doing what?
This is like one day of manufacturing.
Yes, this plant can only make 400 in one day.
Okay.
So S plus G, and then what would the inequality sign be? Less than or equal to 400. Okay, and we don't have any further constraints in this problem. Some problems have 6 constraints, 7 constraints. Okay, it just depends. This one was not so bad. Yes.
Why would you do less than 400 for like less than or equal to for a total?
Okay, because it's saying the largest possible output. Okay. Is 400. So the plant cannot handle any more than 400 in one day.
But it can handle less.
It can handle less, yes. It just can't handle any more. Okay, so now what we're going to do is graph all of our constraints, okay? And so we have to decide, let me see if I can bring these up a little bit here. We have to decide who we're going to put on the y-axis and who we're going to put on the x-axis. And this is totally up to you, so I'll let you guys pick. Do you want graphing or scientific on the y?
Graphic.
You want to put graphing on the y. Okay, so I'm going to put G over here, and I'm going to put S over here.
So for all of these, you can choose.
You can choose, yep. Okay, so the next thing I want to do is, before I start scaling my graph, and I'm telling you this because I've done this so many times, I just start graphing and then I realize I don't have enough points. I'm going to look at my y-intercepts that I'm possibly going to need. So to graph this one over here, I'm going to go ahead and put it into y-intercept form and make it an equation. So it'll just be G is equal to negative S plus 400. All right, which means that's going to give me a y-intercept of 400. Okay, so I know that's the highest that I need to go, and I'm going to go ahead and set that up. Okay, so let's say we start here, and again, everything's in the first quadrant because we don't have negative calculators, and I think I'll just do 20, 40, 60, 80, 100. I'm going by 20s, yeah. 20, 40, 60, 80, 200. 20, 40, 60, 80. Yes, you have a graph on your paper. And 20, 40, 60, 80, 400. Okay, and that same scale is going to work on the other side, so I'm going to do the same thing. 20, 40, 60, 80. 1, 2, 60, 80, 3, and 20, 40, 60, 80, 4. All right. So again, experience has taught me to figure out those intercepts first. Okay, so now what we're going to do, and graphing these in different colors is helpful. All right, so I'm going to try to use lighter colors so it doesn't get so jumbled in here. Alrighty, so one of our constraints is S is greater than or equal to 200. Is that going to be a vertical line or a horizontal line? So where is S? Yeah, this is going to be a vertical line here. We're graphing S is greater than or equal to 200. Okay. All right, so I'm going to graph S right here. Okay, and if it's greater than or equal to that, what side of that line should I shade? To the right. Okay, so I'm going to shade to the right of this. Okay.
How far up does it need to go?
I just went just a little past the 400.
Does it matter?
Well, I only went there because I know that my highest y-intercept was 400.
Oh.
So. Okay. I have another constraint of G.
Just all like technically.
It's technically going on, but yeah, I just went a little ways just to get it down. Okay, I also have G is greater than or equal to 80. Okay, so is that a horizontal or vertical line?
Horizontal.
That's the horizontal. I'm just going to come over here to 80. So that's in here. And let me get that graphed. It's helpful. Okay. And do I want to shade above the 80 or below? Above. Okay. So technically, it would be all of this over here. All right. But again, I'm looking for the overlapping region. So at this point, I'm really so far interested in just this piece up here. Okay, I have one more constraint, and we said that one is G is equal to negative S plus 400. So that's going to be my y-intercept is 400. And it has a slope of -1. That's going to take me down to 400 on the x-axis. And I'm going to connect those.
Whoa.
Sorry, I'm going to have to adjust that one. What's
Oh,
that?
so it's just 400.
It's just 400. Yes, this is.
Why do we just do 400 and 400?
Y-intercept of 400 and a slope of -1. So it's a 1-to-1 relationship going down, or 1 to -1. Okay. And for that one, again, just like we did in that warm-up problem, if I come over to the original and I plug in a point that's not on the line, and again, 0, 0 is the easiest. If I plug in 0, 0, I'm going to get 0 is less than or equal to 400. Is that true?
Yeah.
Yes. So what portion of the line should be shaded? Towards 0, 0 or away? Towards 0, 0. So that's going to be all of this over here. But again, which portion am I interested in?
The overlap.
Where all three of those happen to overlap, which forms the shape of a triangle. Yes. Okay. So we've got this piece in here. Actually, I have a highlighter, so I'll highlight it. Okay.
Oh, so just overlaps in this tiny.
Yes, this tiny little triangle here. And what do we call this overlapping region? Feasible region. Okay, so now I want to look at the corners on my feasible region. And what corners do we see? How many?
3.
There's 3 corners. Okay, we've got one here, and that one is at
280.
280. We've got one here. Let's see, which is at 200. Yep, 200, 200. And we've got one here, which is actually it's 320. 320, 80. Okay. Now, we tried to graph this carefully. Sometimes it doesn't graph out so nicely and you can't really see where the intersection is. What happens when you can't see the intersection? What can we do? Solve it. Yeah, it's just a system of 2 equations. We figure out what the intersection is. Okay, so again, we are after an objective. And what was our objective? Maximize the money, the profit. Okay, so now we're going to pull in our profit equation. And what was that? 25, I can't remember.
25s plus 50.
25s plus 50g. Okay, so 25s plus 50g. Okay, even though there are 3 points here, we can sort of logic out which one is not going to be a max, right? The bottom left, right? Because automatically, if I compare it to the 320/80, it's already less than that one. Or if I compare it to 200/200, it's less than that one. So I'm not going to spend any time testing that point. All right, so now I'm going to test my other 2, and we're just going to plug them in. So P is equal to, if I do 25 times 200 scientific, plus 50 times 200 graphing calculators. Let's see. We get, all right. What's our profit?
15,000.
15,000.
Plus 10,000, right?
Yes.
Oh, so 15,000.
Yes. Okay. So that was testing the point 200, 200. And now we want to test the other point, 320, 80. So P is equal to 25 times 320 plus 50 times 80. And we get a total of, you see that one comes out to 12,000. All right, so what combination of calculators should we make in order to maximize our profit? 200 and 200, okay. So we say 200 of each to maximize the profit of
So 200
15,000.
scientific calculators and 200 graphing calculators?
Yes. Okay. So what do we think of that one?
Long.
Yeah, it is.
But it
But
is-
it was
it
pretty
does
makes sense though.
It
Okay.
makes sense if you understand that one fine.
Yeah. There's a lot going on in
Because I
these.
messed up my graph numbers and then I had to like erase my whole graph.
Yep. So again, remember, you can do this without making a nice, pretty graph. It just means you're going to have to solve your system because it's not always possible to graph it so nicely.
Definitely.
Okay, this one is a little more involved. But can we handle it?
Yeah.
Yes! Alrighty. Alrighty, so Kathy Bees is Chief Mathematician for Fly-By-Night Aircraft Corporation. She's responsible for the mathematical analysis of the manufacturing of the company's 2 models of planes. There's the Sopwith Camel and the larger Sopwith Hippopotamus.
So C and
Yes, thank you. You're already starting. She's already naming them. Let's put those down. So this is going to be C, and this is going to be H. All right. Fly by Night makes a profit of $300 per camel and $200 per hippo. So we want to write an objective equation to represent the total profit. Okay. So profit is equal to
B equals 300C plus 200H.
300C plus 200H. And what is this equation called? Objective function. Do we graph the objective function?
No, we do
No. Okay. We save it. We're not even going to look at it until we get to the end. Okay. Each department has certain restrictions concerning the number of planes which can be manufactured. What do we call these restrictions? Constraints. Beautiful. Okay, so first one, production. No more than 7 hippos and no more than 11 camels can be manufactured per day. So let's look at the hippos first. What's that inequality?
H is less than or equal to 7.
So awesome. And for camels?
C is less than or equal to 11.
Beautiful. All right. Shipping. No more than 12 planes total can be manufactured per day.
H plus C is less than or equal to 12.
Is less than.
Awesome. You guys are rocking it so far. Sales. The number of hippos manufactured per day must be no more than twice the number of camels.
H is less than or equal to 2C.
Okay. All right. Labor. You must use more than 1,000 labor hours per day. It takes 100 hours to manufacture each camel and 200 hours to manufacture each hippo.
100C plus 200H is less than or equal to 5.
Oh, you must use more than
Is
is greater than or equal to 1,000. Okay. I know it says more than, but it's really, we should say at least. Okay. How many hippos and camels should be produced per day to give the greatest feasible profit? And then what is that greatest feasible profit? How many constraints do we have to graph?
5.
Yes, we have a lot. Okay. So hopefully I won't lose track. You know what? I'm going to copy this graph from up here so I have something to go on. Copy. Well, okay, so let's be careful here. Our numbers look pretty small, yes? Except for this one here. So before we start putting in our scale, who are we going to put on the X and who are we going to put on Y?
H on
H on Y.
You want to put H on Y? Okay, so we're going to put H on the Y and C on the X. Okay, so I need to kind of figure out, well, I can see most of these numbers are pretty small. Like this equation here, if H is on the Y, this is going to become H is equal to negative C plus 12. Okay, so that's only 12. I'm going to go ahead and simplify this one down here because this would be 200H is equal to negative 100C plus 1,000. And then what would we have to do? Divide by 200. I'm going to do this down here, which means it becomes H is equal to negative 1/2 C plus 5. Okay, so our numbers are actually not that big this time. Okay, and I just used a humongous graph here, so I'm going to spread this out. So if this is 0, 0, I think I'll do this as 1, 2, 3, 4, 5, 6, 7. Back to that equation? No? Okay. All right. So this will be 1, 2, 3, 4, 5. Oh, I had a y-intercept of 12, didn't I? I did. So let me go a little higher. 8, 9, 10, 11, 12. Okay. So 6, 7, 8, 9, 10, 11, 12. Okay. We got a lot of constraints to graph. All right, so let's look at the first one. H has to be less than or equal to 7. I'm going to do this one in a light color. Less than or equal to 7. Is that going to be a horizontal or vertical line?
That is going to be
Horizontal, along 7. Okay, so let me graph that. And are we shading above this line or below? Below. So this region in here. Okay.
all the way to there.
For now. Okay, and then we also have, I'm going to check these off as we do them. We did this one. That one was in pink. Okay, I'm doing this one in blue. C is less than or equal to 11. So that's going to be horizontal or vertical? Vertical. So that's over here. And are we shading to the left or right of this one?
Left.
To the left.
Is that 11? Oh, 11.
Yes, for the C. Okay. So far, what region are we constrained to?
The triangle.
Yeah, that little rectangle there. Okay, so we've taken care of this one. Alrighty, we also have H is equal to negative C plus 12, so that's a y-intercept of 12, and a slope of negative 1, so that's going to take me to 12 here also. So let me put that in.
It just takes you to the other 12.
Yeah, if it's a slope of negative 1, it's a negative 1-to-1 relationship.
And that's going to be shaded below it, right?
Okay. Well, we'll double check. Look at the original. Pick a point. If I plug in 0, 0, is 0 less than or equal to 12?
Yeah.
Yes. So we do shade towards that direction.
Wait, I'm confused on that. How do you know which way to go?
So go back to the original. Pick a point that's not on the line. So 0, 0 is the perfect point to put in.
Okay.
And if I plug in the original, I get 0 plus 0 is less than or equal to 12. Is that true?
Yeah.
It's true, so we know to shade towards it. If it were false, we would shade away from it. Okay, so it's everything on this side of the line, but I'm not going to shade outside the rectangle because I already know I'm constrained to that rectangle. Okay, let's see. We took care of this one. We've got this one over here. H is less than or equal to 2C. So what we're going to graph on this one is H is equal to 2C, which means what's my y-intercept?
0.
0, and it has a slope of 2. Okay. So y-intercept of 0 and a slope of 2. And I'm really thankful for these built-in lines in here because there's no way I could draw that straight.
H equals just under. Oh.
Less than 2C.
Okay.
That
So, okay, we're going to do a test point. Can we test 0, 0 in this one? No, because it's on the line. So what's a good point we can test?
1, 1.
Let's see, 1, 1. We can test 1, 1. 1, 1 is not on that line. Okay, so if we plug in 1, 1, we're going to get 1 is less than or equal to 2. Is that true?
Yeah.
That is true. So we shade the side towards 1, 1. So that's going to be over here. Yes. Okay, and again, this goes past here, but I'm just going to shade the region that is so far just in the feasible part and not outside. Okay. And, okay, we took care of that one. We have one more. Whew, a lot of constraints, huh? I'm trying to find light colors to put them in so that it doesn't come out so wild. Okay, I guess I will do this one in, I'll do that one in yellow. It's probably going to come out really light. Okay, we have a y-intercept of 5 and a slope of 1/2, negative 1/2. Okay, so that's going to take me over here. And yes.
I forgot that I spaced out how it's 0.51, 1.52.
Mm-hmm.
So I kind of messed up a lot because I forgot that I did.
Okay. Well, again, you can always test your points. It just makes it a little more difficult when the graph doesn't come out right.
How did you get it to 11?
To what?
How did you know it was going to be at 11?
It's a 10.
Is that,
It's a 10. Yes.
oh, well, how did you know it was going to get to 10?
Because it's going down 1 and across 2. So every one that it goes down
okay, so
goes
you
across
just
2.
matched it up.
Yeah.
I thought you automatically knew.
I can't see the lines anymore.
Yes, because there's a lot going on. Okay. What's our test point for this one? 0, 0. So if I plug in 0, 0, I'm going to get 0 is greater than or equal to 1,000. Is that true or false? It's false, so I'm going to shade on the other side. So that's over here. Okay, so I'm going to take a red pen now and kind of mark the feasible region because it's very difficult to see at this point. Okay, so we've got an intersection here. We have 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 an intersection here and here.
There's 3 at that little bottom thing?
Yes.
So there's 2, there's 11, 0, 11, 1.
Mm-hmm.
0.
All right, so I'm going to go ahead and take my highlighter now and highlight all this because I know it's difficult to see. So again, we're looking for where any 2 lines intersect one another around this region. Okay, so do you see why I was trying to use really light colors when I was doing this? Otherwise it gets really difficult to see. Okay, so again, how many vertices did we end up with? 6, but we're going to sort of logic this. I do not want to be testing 6 points. So again, our goal was maximize profit. What was our profit equation again?
300C plus 200H equals
300C plus 200H. Okay. Well, I'm going to mark all of these now, and we'll talk about it. So this one here is at 2, 4. So 2, 4. This one here is at, what's that, 3, 7? Actually, it's 3.57.
What?
Yeah, 3.57. Yeah, this is 3. This is 3.5. This one here is at 5.7. This one here is at 11.1. This one here is at 11.0. And this one here is at 10.0. Okay. So again, I usually start in like my lower left corner. If I compare 2.4 to say 5.7, which one's going to have the higher profit? 5.7. So am I going to test 2.4?
No.
No, it's gone. Out.
And 3.57 is
Yeah, and can you have 3.5 hippos or camels in this case? No. Gone. Okay. Alrighty. 10.0 versus 11.0. 11.0 is the larger one. I'm going to eliminate the 10. 11.0 versus 11.1. 11.1 is going to win. We're not going to test that one. So how many points are we down to? 2. We're only going to test those 2 points there. Yes. If you compare 2.4 to 5.7, which one's going to give you the higher profit? Yeah. Okay, so testing 5.7. P is equal to 300 times 5 plus 200 times 7. And what is that? 1,500 plus 1,400. That means we get a profit of $2,900 if we make that combination. Okay. Testing 11.1, profit is equal to 300 times 11 plus 200 times 1, and that's going to give us 3,300 plus 200. What's our profit there? 3,500. So what combination of planes should we be making? 11. 11.
Oh wait. 11C plus 1H.
11 camels and 1 hippo to maximize profit. Of $3,500. All right, what do we think of that? Okay.
But all I'm gonna make one mistake on like the constraint, and then
Yes, and it gets very frustrating. Okay. Alrighty.
I have a question.
Yes.
So why did we have to like point the 11.0 and the 10.0 too? Like where did those points come from?
Okay, well there is it's sort of an understood, there's an understood constraint here because we're working with physical items. So the understood constraint is that it's not going to be less than 0. Okay. So we didn't graph this one because, again, you're not going to make negative airplanes.
So why didn't we do a point on 0.0?
It's not, yeah, it's not on the region.
Okay.
But if it were on the region, we would put a point there, but we wouldn't bother testing it because it's not going to give us anything. Okay. All right, the next one, I'm going to let you guys work together with your table mates and give that one a try. Okay. These last ones, I'll just put the answers in. Should be welcome.
Of what? Thank you. Oh, this is our homework? Oh, they just didn't take the homework. It's okay.
I don't know where I put anything.
Yeah.
I didn't know keep money.
Reading, right? What? You only have reading?
Yeah, but
It's like basically what she was trying to explain to John.
okay.
It's so funny.
Alright, thank you, Miss
I thought about
Hi.
it so many times after and just started laughing.
That noise is kind of seared into my brain.
I love that sound on TikTok. It's my favorite.
What, the squeaking one?
This is like the epitome of me. Like knowing I have a test right or quiz next. And then like pretending I know everything so I don't have to study. Like why do I do this?